This is the second application of a potentiometer, and this application is to determine the internal resistance of a cell. So the connection circuit for this application, it is as shown in this figure. So as you can see, this part below it, it is the auxiliary circuit, so it is always same. Now the extra components we have added here is RB, which is the resistance box, the cell of EMF E, and another key K2, a galvanometer, and a jockey. Okay, so what we will do here is, again like before, we adjust the positions of the rheostat. We put on the key K1 so that a constant current I will flow through the circuit in this way. Okay, now looking at the figure, it is clearly seen that, just forget about this part above. Now when this key K2, it is keep open. When you open the key number 2, this current I, okay, it cannot go to the resistance box because this key is open, so it stopped till here only. Similarly, the current which is sending by the EMF of the cell, it is going like this. It is going like this. It cannot go to the resistance box. So this resistance box, if you remember, in the chapter of EMF, I have explained to you that if I have a key, if the key is open, if this key is open, then when you measure the potential difference between the two terminals of the cell using a voltmeter, that potential difference is known as EMF. So in this case, because this key here, it is open, so that means no current is passing through the external resistance. Just like here, when this key is open, there is no current passing through this capital R. So the the potential difference between the two terminals stands for the EMF. Okay. So again, I will explain from the beginning, right? We adjust the positions of the rheostat. We close the key K1 while this key K2 is kept open, and the constant current I, it is flowing through the circuit. Similarly, the current from the cell will pass through the circuit like this. It goes to the galvanometer and come back to the cell. Now, you take a jockey and you slide along the wire. You keep on sliding till you get a zero deflection in the galvanometer. So, let's say this jockey, right, it happens that at this point, the galvanometer gives 0. Let us imagine that this length, it is L1. So when the jockey, right, when the galvanometer is 0, it means that the current in the circuit is 0. So when the current in the circuit is 0, what happens is the EMF of the cell, it can't be written as, just like before, KL. But here the EMF is E. Okay, this K is a potential difference, and the L here, it is the length of this part, it is L1. So this is the EMF of the cell when the key K2 is kept open. Okay, now at the same time I will put on the key number 2. Then what happened? I select some resistance from here, because this resistance box, it is actually a box which consists of the resistance of different values. So you can select any resistance that you want from here, and you slide this jockey along the wire again till you get a zero deflection. Suppose it happens that this jockey touch at point G2 and galvanometer gives zero deflection, and this length, it is L2. Okay, so because now there is a current, right? Looking here, look at this figure. This current, it is passing from the cell, it is going like this, it pass to the galvanometer. The key is connected here, so it goes through the resistant box, and in this way it goes the current. Okay, so you can see here that when, just like in this case, when the current it is passing through the external resistance, then the potential difference between the two terminals of the cell, it is known as terminal potential difference, and that is V. So because the current in this case is 0, E is equals to V. So therefore the terminal potential difference when the key K2 is closed is V is equals to, again it should be taking this form, KL2. I hope this is clear. Okay. So now what I will do is I will divide these two. V upon E. V upon E mean KL2 upon KL1. This K with this K cancel. And instead of V, I will write I capital R, which is the potential drop across this resistance. In this case, it is this. And instead of E, EMF, if you remember, E is written as V plus IR. Sorry, V plus I small r. What is this small r? This small r, it is the internal resistance of this cell, and whose value it needs to be determined here. So instead of E, we write V plus IR. So this is okay, I hope. This is L2, this is L1. Now, or I will exchange, okay, again I will do like this, IR, again instead of V, I will write I capital R plus I small r, this is L2 by L1. Next, I will take common this I in the denominator. Inside bracket, I'll have capital R plus small r. This is L2 by L1. Now this capital I can be cancelled. Next, I'm taking the reciprocal in this case, like R plus small r up, capital R down. Similarly, this will change, L up, L2 down. So now I'll split the denominator in this way. This is L1 by L2. Now this R with this R cancel, you get 1. So just small r upon capital R will be equals to L1 by L2. And this one, take to the right, it become minus. So R is equals to L1, taking the LCM, in this case you will get this much. And with this capital R, it goes there. Okay. So this is the equation for the internal resistance of a cell. Okay, look at this equation. L1 and L2, they are unknown quantities because they can be found out from the scale. Similarly, this R, as I told you, it is the resistance from the box. So this is also known. So all quantities which are there in the right hand side of these equations, they are known quantities. So therefore, this small r can be determined using this equation. So this is how we use a potentiometer to find out the internal resistance of a cell.